Here we are with section 10. Couple quick words before we dive into some modeling problems, specifically about modeling. It is not where functions put on fancy clothes and maybe a little makeup and head down the runway or get their photo taken. No, that's modeling with people. Modeling with functions has a little different meaning. It's where you've got data from a real life scenario and you kind of want to find an equation, in our case a function, to represent that situation so that you can find information, make decisions, and make predictions. Okay, whenever you hear that term in Precalc, modeling, that's what it's referring to. Here's a scenario from a real life context. Let's find an equation that is as good a representation as we can find of what's going on with those numbers. Okay? I'll spend a decent amount of time on it and work through several examples in this lesson because I think it's an important topic. It really gets at one of the most important things that functions do for us. This is kind of why we study them. This is largely why they're valuable. All right, you're going to see references to two different types of models, direct and inverse. I'm going to work through a couple direct models to get going. Now, we've worked with models so far in this unit quite a bit, actually. The difference now is we're given some information and we're typically going to write what the equation is. Okay? Direct models usually follow some structure of this. Y equals k times x, where k is a constant, and in fact it's the constant that we're looking for. It's the constant we'd like to find. One of the most overlooked components of modeling, and again, if you read all the word problems that you've done in this chapter, every single one of them does this. It defines what the variables are. Okay? I just stuck with x and y. You know, you could have called this income and tax. Okay? I just want you to be clear on what things you have to define. Each of these equations is going to have two variables, an x and a y, and we have to be very careful to say what they are. Otherwise, the problem could be very misleading or confusing. The way I'm going to set this up is I'm going to say that x is somebody's income. Now, I will allow you to be I'm not going to be super picky on a test when you're defining your variables. Could I define it better than to just say it's income in dollars? I certainly could. Right? I could be more thorough and say it's an individual's income in the state of Pennsylvania. You know, I could specify that this problem is about Pennsylvania. You know, the biggest thing I'm concerned about in these problems is that, you know, if you don't even attempt to define your variables, that's not good. You got to make sure you do it. So I'm not going to be super picky about it. Then right here for y, if you were to just tell me that's the tax deduction in dollars. Okay? What you see there for me would work. Okay, it makes it clear what your variables are here. Now, to get the model, we always have to have some information. And it's got to be enough to figure out what this constant is. This is a fairly simple direct model, so we don't need a ton. We have this one individual. This particular month, they made $1,500. Their state income tax was $46.05. You know, essentially what K becomes is, it's the rate. It's the rate. Got to solve for k. You divide both sides by 1,500 and you would get 0.0307. And now to go back to finish my model, y, which I've already said is your tax deduction, is going to be 0.0307 times x, which would be your income. It's essentially saying that in Pennsylvania, for this particular, whenever this was, because tax rates can change, you know, the process of doing it can be tricky, but they do. But at the time this book was written, Pennsylvania's state tax rate was 3.07%. My guess would be since then it's probably gone up. That's a fairly low rate. All right, that last example was linear. And I want to show you this one. It's another direct model. I'm going to use distance and time, but you can see from the wording it's directly proportional to the square of the time it rolls. So this is related to t squared, not just t. And if I just showed you linear examples like the last one, I'd be concerned that you think that, oh, the x variable is always just x. Well, no, this is going to be more like a quadratic model because t is squared. And that's certainly possible to have a direct model that falls under that category. Next step here that just needs to happen is t and d. Okay? And again, you could make a good case here that I should be more thorough. I would be okay if you have this, that t is time in seconds, and d is distance in feet. I would be okay if you put that. Okay? Again, some would see this and say, no, you need to be way more thorough than that. It's time after the ball is released, and the distance is the distance that the ball rolled down the incline, or decline, I guess you could say. I'm okay with this. If you're just saying the two things, that t is time, measured in seconds, and that d is distance, measured in feet, I'm okay with kind of looking at the context of the problem. You know, that this is about the ball rolling, right? I'm okay with that. Again, just don't forget to do it. Make sure you define your variables. Need some information, and we actually have some great information to get k. Really the best piece of information we could want. After 1 second, it went 8 feet. This just solves beautifully. And we get that k is 8. Now to finish off part A, the distance the ball rolled is 8t squared. Okay? That equation is what we would call a model for this situation. Follow-up question here is relatively simple. What's the distance if t is 3? Okay. Now the reason we had to square t is that the rate that the ball is rolling is not a constant. As it's rolling down this incline, it's rolling faster and faster and faster. So notice in the first second that it told us the ball went 8 feet. That doesn't mean this answer is going to be 24. It's not just rolling 8 feet per second. From second number 1 to 2, it rolled even farther. And from 2 to 3, it's going to roll even farther. After 3 seconds, we're all the way down to 72 feet. Okay? That's the effect of gravity rolling down this inclined plane, is that, you know, this ball is going to be, you know, it's going to cause it to roll faster and faster. All right, so now let's kind of give ourselves some structure in terms of what we're doing here. What we've seen are again, direct models. I already kind of gave you the framework of that. And again, the definition I'm giving here is that x is to the first power. We just saw one where x was squared. So the variable can take on an exponent. It just means that you're going to have nonlinear data, which is fine because the goal is still to find k. Okay? In a problem like that, k is going to be a constant. And for a model that's going to be direct, here's what you need to be thinking. I want this set up so that as x increases, y increases. Those two variables need to go up together. Both examples were direct. You make more money in the state of Pennsylvania, your tax deduction is bigger. Okay, it's 3.07% of whatever you made. That goes up, the tax deduction goes up. The example with the ball rolling, as t goes up, so did d. The more time that went by, the farther the ball rolled. Okay? To contrast that, we'd have an inverse, which should be structured something like this. There's a lot of different ways to write an inverse model. This is kind of the way we're going to do it. What that's going to tell you is, well, number one, and that's what most of these problems are focusing on, is you've got this constant involved in the problem, and we need to figure out what it is. Okay? But these examples are set up as x goes up, y goes down. Okay? That's an inverse. And you'll come across variables all the time that are related in that way. As one gets bigger, the other gets smaller. This is a little bit more complicated. Little bit. Okay? Because this has both. And I want you to see one of these because it kind of represents about how tricky these problems could get for us. But here's the structure I'd have to apply to this. Okay? This relates some factors back to the volume of a gas. I've got some constant that I'm looking for. But it says that the volume of a gas is varies directly as the temperature. Okay? But inversely to pressure. Notice how many variables we have here to define. Volume, temp, pressure. Okay? This one has three. It's relating volume back to these other things, but here's the deal with this law of gas. The volume of the gas will go up as the temperature goes up, right? If it's heated, it's going to expand and take up more space. If pressure is applied to it, onto the gas, it'll take up less space. Temp goes up, volume goes up. However, if pressure on the gas goes up, volume goes down. Here's volume. You do have to be particular on this one about units. I'm not super concerned, about them. I just want to make sure that we're clear on this whole problem what we're measuring stuff in. Okay? Volume has to be in cubic centimeters. T is temperature. And my favorite scale, the old Kelvin scale, everybody loves that, where 0 isn't just a chilly January day. No. 0 is absolute 0. Molecules stop moving altogether. And then, let's see here, pressure. And this is in kilograms per centimeter squared. Like, that's even one for me. I'm not really familiar with physics and pressure. Apparently, kilograms per cubic centimeter. I don't know that unit of measurement all that well, but for this problem, I just want to make sure that I stated it. That's what pressure is being measured in. From there, I'm good. Okay. Gives us some data about a scenario where the gas is taking up 8,000 cubic centimeters. There's K. Temp is 294. And pressure is 0.75. Multiply both sides by 0.75, and you get 6,000 is K times 294. You could leave this as a fraction. 6,000 over 294, I think it simplifies to 1,000 over 49. And that's fine if you leave it like that. That's a little better answer than 20.41. I'm going to use this to get some information in the next part. And if you leave the answer as a fraction, it just gets harder to solve in the next part. And it's not going to give you that much more accuracy. So we got the constant that relates all these variables. It's about 20.41. So now let's head down here. All right, another scenario is that we've now got some gas. We've got some gas. But we also have the constant. And we have the temperature. The pressure. Well, that was nice of them. They gave us the most difficult variable to find. That was so sweet of them. That's fine. We're up for it. Everything is just where it goes. I got 7,000 in for volume, 300 in for temperature. The constant applies to any problem that involves this gas law. Let's move that variable over here. Pressure times 7,000 equals 20.41 times 300. That could just be simplified and punched into a calculator. But just to finish it off here, I divide by 7,000. I could hold off and just go to my calculator at once and do 20.41 times 300, make sure that's in parentheses, because then I want to divide by 7,000. And we get like 0.87 kilograms per centimeter squared. And there you have it. Okay. Good example to see, a little bit trickier. Again, what's going on there is we had 3 variables instead of 2. Volume was directly related to temperature, but also inversely related to pressure. Both different models kind of going on at the same time. Good example to study off of. I probably wouldn't give you one that's a whole lot trickier than that one. That's about as tough as it would get, so good one to study. All right, joint variation, notice it doesn't specify here direct or inverse. Joint just means there's multiple variables going on. Simple interest is your principal times your rate times time. Okay, and notice from the information I was given, this is kind of like K. I need to find this rate. So what this problem is saying, because it says joint variation, is we need to define that I is interest measured in dollars. P is principal. This would be stuff, not the variables, but as far as the principal, the definitions of principal and interest, I would give that to you on a test. I find principal is the one students are the least familiar with, that's the amount of money that was either invested or put in the savings account in the first place. Okay, we want to distinguish these two because the interest tells us how well the account is doing, how much money are we making off it. Okay, because we're not going to make money off this account by just putting more money into it. We certainly can, but the interest, if the savings account is somehow involving investments, the interest is going to be the measure as to how well it's doing, right? How is that money growing over time as it's been invested? Time. Perfect. Let's talk about time. That's T. Time is in years. Okay? This just implies that it's a savings account. It doesn't really say what type. Lots of different savings accounts. Some that you have more access to the money, some that you have less. Some like retirement accounts that you put money into a little bit over a very, very long period of time and you want a substantial amount of growth, and you don't take money out of it until, you're all old and stuff and can't work anymore or don't want to work anymore. That's why time for this one's measured in years. Might be a long, you might let this account grow for a long time. Let's just throw R on there. Why not? That's what we're finding. It's our interest rate. It's going to be measured essentially as a percent. Now, if we take all this stuff that we have, here's the deal. It did tell me some wonderful stuff that it earned $43.75 off of an original investment of $5,000. The rate, no go, didn't tell me. And it made this amount after just 3 months, or 1/4 of a year. Notice I specified that time has to be in years. And the reason those units become important for us, if we're going to put in a number for t, we got to make sure it's measured in years. If they told us that it was just 3 months, you might think, just put in 3. Well, that's fine. You can put in 3. But if you were to do that, that's going to tell you the growth over 3 years, not 3 months. So I got to put 1/4. All right, we got a little bit of work here to solve this one. First step would probably be divide by 1/4. Essentially, you'd be multiplying by 4. And back over here, we would have 5,000 times R. To get R by itself, I would have to divide by 5,000, and I'm all set up that I have got my interest rate, which I believe comes out to be something very close to that, to 0.035, or 3.5% is what we're talking about. Okay, we earned 3.5% of the original investment in the first 3 months. Well, not quite. That would be the rate of what we would expect to earn per year. Okay. We got 1/4 of that in the first 3 months. All right, so we found R, and now we're in really good shape to use this because it gives us this scenario. That now, if we're working with interest, we just need principal. And for the rest of this problem, we're going to treat our rate as a constant. So that's all we need now. The circumstances of this problem are not changing. We're still talking about the same original investment. So we're looking for interest, so P is going to be 5,000, and whoops. That would have come out to be a little bit of a different answer if we got 35% per year instead of 3.5. And now it says after 3/4 of a year, so we got to put 3/4 or 0.75. Don't have to do any solving here because this formula is set up to get interest. So we just essentially have to plug some numbers in. And when it's all said and done, we got $131.25. All right. Again, joint variation in this problem. Both variables were direct, but what's going on here is interest is directly related to more than one thing. How much did you invest? That's principal. What's the interest rate? R. And how much time was given for the investment to grow, which is what we call T. So you can have models that look at a variable being related to multiple factors. That's what's going on here.